So I want you to imagine buying $1 million state-of-the-art sports car engine.
Oh, yeah. An absolute marvel of modern engineering.
Right. It's incredibly efficient. It's powerful. You are just totally thrilled with it. But then you take that pristine engine and you drop it into a rusted-out chassis that is, guaranteed to collapse in just a few years.
Which completely defeats the purpose of the engine.
Exactly.
Yeah.
I mean, it doesn't matter how good the engine is if the car simply falls apart underneath it.
Yeah.
And the crazy part is that is exactly what we are doing with some of the biggest solar energy projects in the world right now.
It's a massive blind spot in the industry.
It really is. Because when you think about the massive boom in solar energy, everything from those sleek panels on residential roofs to the massive multi-megawatt solar parks sprawling out across India, we almost entirely focus on the shiny stuff.
The panels themselves.
Yeah, we obsess over the photovoltaic modules, the high-tech inverters, the battery storage, but we almost universally ignore the literal foundation holding it all up in the air, which is the mounting structures.
Yeah, the structural framework is really the classic invisible architecture. I mean, the components doing the absolute heaviest lifting rarely get the spotlight.
Right.
And for EPC contractors, the engineering, procurement, and construction firms and the massive project developers who are funding these builds, ignoring that foundation is just a catastrophic financial risk.
Because it's not just holding up some glass.
Exactly.
Yeah.
Picking a mounting structure isn't just about walking into a hardware store and grabbing the heaviest metal off the shelf. It requires guaranteeing long-term reliability and, frankly, strict sustainability compliance over a multi-decade timeline.
And often in brutally unforgiving environments, right?
Oh, absolutely. The elements are relentless.
So to really understand what's at stake here, we're pulling from this really fascinating industry guide published by Eleanor Industries. They're a leading extruded aluminum products manufacturer out of India, and their guide is essentially a mission to settle this massive engineering debate.
A debate that basically dictates the structural integrity, the durability, and the ultimate return on investment for the entire solar industry.
Yeah. So for today's deep dive, we are putting aluminum solar profiles head-to-head against steel structures.
It's a heavy matchup, literally.
Right. But before we can crown a winner, we need to look under the hood at what these two materials actually are. The guide focuses heavily on 6000 series aluminum versus galvanized steel. So let's start with the aluminum side.
Sure.
What makes a solar profile different from, say, a soda can?
Well, the metal used in these utility projects is highly, highly engineered. When we say 6000 series aluminum alloys, we're talking about a very specific metallurgical recipe.
Okay, like a blend.
Right, because pure aluminum is actually quite soft, so they alloy it, they mix it with elements like magnesium and silicon.
Why those two specifically?
So the magnesium provides this robust baseline of strength, while the silicon makes the metal highly pliable when it's heated up.
Oh, I see.
Yeah, and this is crucial because these mounting structures aren't just flat sheets of metal, they are precision extruded.
Extruded meaning? Like pushing Play-Doh through a mold.
Basically, yeah. That means the hot aluminum is forced through a custom-shaped mold, or die, to create highly complex, continuous shapes.
Wow.
So we're talking about intricately designed mounting rails with, built-in channels, specialized clamps, and structural support booms. It's a cohesive, fully engineered ecosystem designed to interlock perfectly.
Okay, let's unpack this.
Yeah.
Because on the other side of the ring, we have steel.
Right, the traditional heavyweight.
Yeah. And the guide notes that steel structures in solar projects are usually fabricated from mild or galvanized steel. They use a hot-dip galvanization process.
Which is pretty intense.
Yeah, it essentially means taking the raw steel and submerging it into a boiling vat of molten zinc to give it a protective coating.
Exactly.
And the primary selling point for steel is its incredible tensile strength, the sheer amount of pulling, stretching, and weight it can handle before it snaps. So I have to push back here.
Sure, go ahead.
If steel has that raw, measurable, higher tensile strength, shouldn't it just be the automatic default? I mean, we're building multi-million-dollar power plants. Why would engineers even bother designing a complex aluminum profile at all if steel is inherently stronger?
Well, the flaw in that logic is assuming a solar panel mount needs the exact same structural properties as, say, a suspension bridge.
Right. It's not holding up cars.
Exactly. In structural engineering, solving for absolute maximum strength is often incredibly inefficient. The real goal is load optimization.
Load optimization, meaning?
Yes, a thick steel beam has higher raw tensile strength than an aluminum rail. But a solar array doesn't need to hold up a skyscraper. Modern aluminium solar systems are heavily engineered to withstand the specific forces they'll actually encounter.
Like wind and weather.
Yeah, things like severe wind shear, where gale force winds are literally trying to rip the panels off a roof, or seismic loads during an earthquake.
Oh.
Aluminium provides exactly the necessary strength to handle those specific environmental stresses, but it does so while offering a massive, undeniable weight advantage over steel.
So it isn't about surviving a hypothetical wrecking ball. It's about surviving a specific gust of wind without adding, completely unnecessary bulk to the project.
Right, which brings up the whole concept of dead load.
Dead load.
Yeah, dead load is the constant, permanent weight of the structural framework itself, just pressing down on a building before a single gust of wind even hits it, or a single drop of rainfall.
Oh, wow. So just sitting there, it's a strain.
Exactly. And aluminium is roughly 1/3 the weight of steel.
That is a massive difference.
Huge. In a real-world application, particularly on a commercial rooftop, you are drastically reducing that dead load. You're putting far less physical stress on the existing architecture of the building.
I mean, I'm just trying to picture this logistics chain, and the weight difference has to ripple out far beyond just the roof itself.
Well, it changes everything.
Because if you're a developer, moving thousands of pounds of steel around a dusty job site requires serious infrastructure. You need heavy-duty flatbeds, massive cranes, large crews, just to muscle the beams into place.
Yeah, it's a major operation.
But with lightweight aluminum rails, two workers can easily carry a 20-foot section across a roof by hand.
Easily. It completely changes the required labor force.
But, raw strength and weight in a vacuum don't matter if the structure rusts away in the rain. Let's look at how these materials actually survive the war of the elements out in the real world.
Yeah, the vulnerability to the elements is perhaps the most critical engineering difference between the two materials.
Because steel rusts.
Right. Steel is fundamentally vulnerable to oxygen and moisture. It desperately wants to rust.
Hence the boiling vat of zinc.
Exactly. That's why the hot dip galvanization process you mentioned earlier is required. The steel relies entirely on that applied shield of zinc to survive.
So the zinc is like...
The zinc acts as a sacrificial bodyguard.
Oh, I like that.
It takes the hit from the rain, the salt, and the humidity, so the steel underneath doesn't have to.
But if that coating degrades...
Or gets scratched by a tool during installation or simply wears down over time, the underlying steel is immediately exposed to the air.
And then what?
Exposed steel begins to corrode and weaken almost instantly, and this degradation accelerates dramatically in coastal areas with high salinity in the air or in tropical regions with constant humidity.
It's like sending someone out into a blizzard wearing a heavy winter coat, but the coat is slowly dissolving.
That's a great way to put it.
Once the coat has holes in it, the person's going to freeze. The steel is wearing a zinc coat, and the environment is constantly trying to tear it off.
So how does aluminium handle that same environment? Because you don't typically see galvanized aluminium.
You don't, because aluminium does something really remarkable when exposed to the elements. It doesn't wear a bodyguard, it protects itself.
Wait, really? When raw aluminium is exposed to oxygen, it undergoes this instant chemical reaction, forming a microscopic, incredibly tough layer of aluminium oxide across its entire surface.
So it essentially scabs over.
Yes, it scabs over. This oxide layer seals the underlying metal away from the elements. And if you scratch aluminium, it simply reacts with the oxygen and forms a new scab over the scratch instantly.
That is wild.
Because of this mechanism, it will not rust in the way steel does. It never requires repainting. It never requires chemical recoating teams to come out every 5 years to maintain its structural integrity against the weather.
Which naturally dictates the ultimate lifespan of these setups.
Precisely.
Because the guide notes that due to this self-healing oxide layer, a well-designed aluminum structure easily lasts 25 years or more in the field.
Easily.
While steel, because of the inevitable degradation of that zinc bodyguard, generally starts to fail much faster, usually requiring major intervention around the 15 to 20-year mark.
And what's fascinating here is how that 25-year lifespan for an aluminium structure perfectly aligns with the standard performance warranties and expected life cycle of the solar panels themselves.
Oh, that makes so much sense.
Right. Think about the operational continuity that creates for a power plant. The skeletal framework and the energy-generating organs age at the exact same rate.
Because with steel, it's out of sync.
Exactly. With steel, because it degrades faster than the panels, developers frequently run into catastrophic maintenance scenarios.
I can only imagine.
Imagine reaching year 15 of a 25-year power purchase agreement. The steel beams are heavily rusted. You literally have to hire crews, bring in heavy cranes, disconnect the high voltage wiring,
Oh, wow.
and completely dismantle perfectly functioning solar panels just to pull out the rusted steel support beams underneath them.
That sounds like an absolute logistical nightmare. You are tearing apart a live power plant, completely halting your energy generation and your revenue stream, just to fix the scaffolding holding it up.
It's a huge disruption.
Well, wait, this brings up a massive contradiction.
Okay, let's hear it.
If aluminium is vastly lighter, if it naturally scabs over and is immune to rust, and if it saves developers from a multi-million-dollar teardown at year 15, why isn't everyone just using aluminium 100% of the time? There has to be a catch.
Well, the catch is the initial procurement budget.
Ah, money.
Always money. If you only look at the upfront price tag, steel looks incredibly attractive to a purchasing department. Per kilogram, raw steel is significantly cheaper than raw aluminium.
Okay, so when an EPC contractor is trying to submit the lowest possible bid to win a massive utility project, that initial raw material line item can be the deciding factor.
Exactly. The spreadsheet logic initially favors steel.
Okay, but here's where it gets really interesting. Because the Eleanor Industries guide breaks down how buying the cheaper metal actually costs you more money in the long run.
Right. They focus on a metric called the total cost of ownership.
It completely flips the standard bargain hunting logic on its head.
It really does. The initial material cost is only one fraction of the actual cost to build and run a solar plant. Let's look at the installation phase.
Okay.
Because the aluminium systems rely on that precision extrusion we discussed earlier, the parts arrive on-site engineered to fit together seamlessly.
Because of the complex dies.
Right. The extrusion process allows manufacturers to build intricate T-channels right into the rails. Workers simply slide specialized nuts and clamps directly into the rails and tighten them down.
It goes together like a high-tech Lego set.
Exactly like a Lego set. Steel, on the other hand, is often much more labor-intensive. It might require on-site drilling, which compromises the galvanization, or heavy bolting.
So by paying more for the raw aluminium up front, you are drastically slashing your on-site labor hours.
Hugely.
You're renting fewer cranes because the material is light. Your teams are moving twice as fast because the extruded pieces just click together. And your power plant gets commissioned and starts generating electricity much earlier.
And the savings compound even further when you extend that total cost of ownership calculation out over the 25-year lifespan.
How so?
With a steel structure, a developer must budget heavily for ongoing maintenance. They have to pay inspection teams to go out into the field, identify rust spots, manually clean the degrading steel, and reapply harsh anti-corrosive chemicals.
Every few years.
Yes. That is a permanent operational expense dragging down the project's profitability every single year.
But aluminium doesn't need that.
Aluminium, thanks to its natural oxide layer, is virtually zero maintenance.
Wow.
So when you factor in the massive savings on installation labor, the reduced heavy machinery rentals, and a quarter-century of maintenance-free operation, the long-term economic math heavily favors aluminium.
I mean, I am trying to picture this on a massive commercial factory roof. If you've got thousands of panels going up on an industrial warehouse, surely the dead load of heavy steel would literally require the building owner to reinforce the actual foundation of the warehouse just to hold the solar array up.
Which would completely kill the budget of the project.
Right. This means the choice of material isn't just about preference. The physical location of the project dictates the engineering. Let's look at how these materials are actually deployed in real-world scenarios, starting with rooftops.
Well, for residential rooftops, homes simply have very limited load-bearing capacity. You cannot drop a massive, heavy steel framework onto a standard timber roof without risking severe structural damage.
Right, nobody wants their roof caving in for solar.
Exactly. Aluminium's lightweight profile is mandatory here, combined with the fact that residential installers need to get on and off a homeowner's roof as quickly as possible. The fast, Lego-like installation minimizes disruption.
And for those massive commercial warehouses and factory sheds.
Engineering stakes are exponentially higher there. Large industrial sheds are built to strict, mathematically calculated load limitations.
So they can't just take extra weight.
No, adding thousands of pounds of steel could instantly violate the building's safety codes and regulatory compliance.
Makes sense.
Furthermore, an active business cannot afford to shut down its operations or clear its factory floor for weeks while a slow, heavy steel installation takes place overhead. Aluminium allows for rapid, lightweight deployment over enormous roof spans.
And what about the weather factor for those factories?
Crucially, many large industrial zones are situated near ports, in coastal belts, or in humid environments. The long-term corrosion resistance of aluminium guarantees that the structural framework survives the harsh environment without requiring a maintenance crew to constantly disrupt the factory's operations to paint rusted beams.
Wait, if aluminium wins the total cost of ownership math, and it completely dominates both residential and industrial rooftops, where does steel actually fit into the modern solar landscape? There has to be a scenario where steel still makes sense.
Steel still holds a significant portion of the market in large-scale utility solar plants.
The huge ones out in the middle of nowhere.
Yep, exactly. These are the massive ground-mounted fields of panels you see stretching to the horizon. In a ground-mounted system, the structural load is driven directly into the earth, so the heavy weight of steel is no longer a structural penalty for a building.
Because the ground can handle the weight.
Right, and because the scale of these utility plants is so unimaginably vast, sometimes covering thousands of acres, that cheaper upfront raw material costs of steel becomes a massive lever in the initial financing.
So they just use steel everywhere on those.
Not everywhere. Often, developers rely on a hybrid model for these mega projects to balance the budget.
A hybrid model meaning they mix the materials on the same mounting structure.
Precisely. They'll use heavy galvanized steel posts and ram them deep into the dirt to serve as the foundation, taking advantage of steel's cheap bulk and raw strength.
Okay.
But then they will bolt precision extruded aluminum rails on top of those steel posts to actually mount and align the delicate solar panels, taking advantage of aluminum's perfect tolerances and fast installation.
Okay, best of both worlds. Cheap, heavy roots in the ground, and a lightweight, precise canopy on top, holding the technology.
That's the idea.
But the Eleanor Guide highlights a massive exception to that rule.
Yeah.
Even for ground-mounted mega plants, the hybrid model completely falls apart depending on the weather.
Oh, absolutely. The local environment always has the final say.
How so?
Developers building utility plants in harsh environments, such as high salinity coastal belts, tropical regions with relentless monsoon rainfall, or highly abrasive deserts.
Oh, deserts.
Yeah, in highly abrasive deserts, the blowing sand physically strips the zinc coating off the metal.
Wow, just sands it right off.
Literally. So in those areas, developers are increasingly pivoting entirely away from steel. They've learned the hard way that the environment will destroy the steel's sacrificial bodyguard in just a few years.
And then the rust starts.
Right. And replacing tens of thousands of deeply anchored, rusted steel posts in the middle of a desert at year 15 completely destroys the long-term financial model of the power plant. So avoiding that catastrophic, predictable degradation forces the complete shift to an all-aluminum ground structure.
Which brings us to the manufacturing realities of actually pulling off a project of that scale. Because if a developer decides to use aluminium for an entire desert solar farm, they aren't just buying off-the-shelf pipes.
Not at all.
The precision we talked about earlier requires a massive industrial partner.
Yeah, working with an experienced, large-scale custom extrusion manufacturer like Eleanor Industries becomes the linchpin of the entire operation.
Because they make the custom parts.
Exactly. A dedicated manufacturer can engineer completely custom extrusion dies. If a developer needs a specific aerodynamic profile to handle localized wind shear or a unique clamping mechanism for a new type of solar panel, the manufacturer pushes the aluminium through that custom shape.
It's all tailored.
Highly tailored. Furthermore, while aluminium naturally forms its own protective oxide scab, a massive manufacturing facility can enhance that protection through a process called anodizing.
Anodizing. How does anodizing work? Is it just another applied coating like galvanizing?
No, it's actually an electrochemical process. Instead of painting a protective layer on top of the metal, anodizing uses electricity and an acid bath to artificially force the aluminium to grow a much thicker, harder version of its natural oxide scab.
Oh, that is cool.
It's incredible. It integrates the protection directly into the molecular structure of the metal itself, making it incredibly resilient for those extreme coastal or desert environments.
So it's not a coating that can peel off, it's just superpowered aluminum.
Exactly. And manufacturers can also apply specialized powder coating if specific aesthetic or environmental compliances are required. But the sheer scale is also a factor.
Right, we're talking huge projects.
A multi-megawatt plant requires thousands upon thousands of perfectly identical, perfectly engineered aluminum pieces arriving on site via bulk distribution exactly when the labor force is ready to install them.
There is one last element the guide touches on, and it steps slightly outside the raw engineering and into the boardroom.
The ESG targets.
Yeah, the choice between steel and aluminum intersects heavily with global ESG targets, environmental, social, and governance goals. Because, let's be honest, the entire fundamental purpose of building a massive solar plant is to generate green, clean energy.
Right. And if we connect this to the bigger picture, the sustainability of the infrastructure itself is under intense scrutiny.
As it should be.
Aluminum is highly recyclable. At the end of a power plant's 25 or 30-year life cycle, when the site is finally decommissioned, that entire aluminum structural framework can be dismantled, melted down, and infinitely repurposed into new extrusions without losing any of its fundamental metallurgical properties.
Infinite recyclability.
Yes. Combine that infinite recyclability with the incredibly low maintenance footprint, meaning no maintenance crews spraying harsh chemical anti-corrosive coatings into the local soil and groundwater every 5 years.
Oh, true. I didn't even think about the chemicals leaking into the soil.
It's a huge issue. So choosing aluminum actively ensures that green certified energy projects actually maintain their environmental integrity across their entire operational life cycle.
It is the stark difference between merely building a green energy source and actually building a green energy source sustainably.
Precisely.
So what does this all mean? If we look at the final verdict from the engineering front lines, steel absolutely still has a place, specifically in low-budget, heavy-load, ground-mounted utility projects, where the soil is forgiving and the upfront cost dictates the financing.
Yeah, it still works there.
But aluminum completely dominates the residential and commercial rooftops. It is mandatory for corrosive coastal and humid environments, and it is the clear winner for developers looking at long-term investments due to its self-healing corrosion resistance and a vastly superior food downtown. Total cost of ownership.
The math just makes sense over time.
It really does. So next time you drive past a solar array, whether it's sitting quietly on your new highway, exactly why the metal underneath those panels looks the way it does, and you'll understand the complex economic and environmental chess match that put it there.
You know, this raises an important question, and it's one we'll thinking about long after we finish this deep dive.
Yeah.
As a society, we spend an enormous amount of time, capital, and energy obsessing over the sustainability and the conversion efficiency of the solar panels themselves. We demand that they generate the cleanest energy possible.
Right, the panels get all the glory.
They do. But if we mount those green panels on materials that require constant toxic chemical recoating to survive the rain, materials that demand regular heavy machinery maintenance that burns diesel fuel, and materials that face a total landfill-bound replacement every 15 years, are we quietly undermining the very environmental mission we are trying to achieve? How green can a solar project truly be if its skeleton isn't built to last?